A big change happened. In the world of computers, it started more than 30 years ago, but most people only saw it recently. The change is a program called ChatGPT. Many people now use it every day. It can write stories. It can answer hard questions. It can help you with your work. This video tells the story of how it was made. It is a long journey. It starts with simple ideas. These ideas grew from small tests into giant systems. This story is for everyone. It will name leaders and companies shaping AI. What does it mean when our machines can think and talk? The story of ChatGPT, and indeed all modern AI, begins not with a grand vision of artificial consciousness, but with a surprisingly simple, almost humble idea: prediction. It's a concept deeply woven into the fabric of our own intelligence. Imagine reading a sentence. As your eyes move across the page, your brain isn't just passively absorbing words. It's racing ahead, constantly forming and testing hypotheses about what comes next. If you read, "The sun rises in the s," your mind instantly supplies the word east. This isn't a conscious calculation. It's a deeply ingrained act of prediction, honed by a lifetime of experience with language and the world. This predictive process is the very essence of comprehension. In the burgeoning field of artificial intelligence, pioneering scientists looked at this fundamental human trait and asked a transformative question. Could a computer be taught to do the same? Could a machine, fed with enough text, learn to anticipate the next word in a sequence? The hypothesis was profound. If a computer can consistently and accurately guess the next word, it can't just be memorizing. It must, by necessity, be learning the underlying patterns, the grammatical rules, the syntactical structures, and even the contextual relationships that govern language. It would have to learn that king is to queen as man is to woman, not because it was explicitly told, but because those patterns emerge from the statistical tapestry of human text. This simple task, predicting the next word, became a powerful, self-correcting teacher. Every prediction was a test. If the model guessed correctly, its internal connections were reinforced. If it guessed wrong, it would adjust its parameters to make a better prediction next time. Millions, then billions of times over. With this method, the data itself became the curriculum, and the vast, ever-expanding library of the internet became the ultimate textbook. Every book, every article, every conversation ever digitized was a potential lesson in the structure of human thought and expression. But this revolutionary idea is not as new as it might seem. Its roots stretch back decades to the 1980s, a time when the computational power needed to realize its full potential was still the stuff of science fiction. In 1986, a researcher named Michael Jordan, no relation to the basketball legend, began training small, primitive networks to learn and reproduce sequences. He demonstrated that a network could observe a pattern and learn to continue it, effectively learning from its own recent past to inform its future. This was a critical step. To achieve this, he introduced a groundbreaking architecture that gave the network a kind of memory. It was called a recurrent neural network, or RNN. By feeding its own output back into itself as input, the network could maintain a state, a memory of what came before, allowing it to understand sequences in a way previous models could not. Crucially, the network didn't just memorize the sequences it saw. It generalized. It extracted the abstract rules governing the pattern. It learned the of counting, or the of the alphabet, rather than just replaying a recording. In essence, it was compressing vast amounts of experience into an efficient internal model, a small but powerful map of meaning. This compression was key. It forced the model to find the most elegant and fundamental principles within the data. In the early 1990s, another researcher, Jeffrey Ellman, took these ideas even further. He fed his own recurrent network a continuous stream of characters from simple English sentences, with no spaces or punctuation. The task was the same: simply predict the next character. The result was astonishing. After training, Elman's network had not only learned to predict characters, but in doing so, it had implicitly learned to identify word boundaries on its own. It figured out where one word ended and another began, simply by observing which sequences of letters were most probable. It was a powerful demonstration that, hidden within the simple goal of prediction, lay the path to a much deeper understanding of language itself. After the first experiments, things were quiet for a while. Computers and datasets were too small. Progress was slow. Researchers solved toy problems, not real-world tasks. Networks forgot long contexts, the vanishing gradient problem. But inside, networks grouped words by meaning, all on their own. Meaning emerged from context, statistics of language. This idea is central to how ChatGPT works today. For years, these were papers and prototypes, not products. AI was fragmented into specialized systems. A single general-purpose model felt far away. But the foundation was set. The breakthrough was coming. And then a new way to see words changed everything. In 2017, Google introduced the transformer with self-attention. Old RNNs squeezed meaning into tiny memory. Transformers looked at everything at once. Self-attention weighs the most relevant words for each position. So bank means riverbank, not money vault. It links meaning across long distances, keeping context intact. Parallel processing made training much faster and larger. OpenAI applied transformers to next word prediction at scale. This combination unlocked large language models. Transformer was the engine, the internet was the fuel. Next, GPT begins, from research to remarkable results. OpenAI released GPT in 2018, Generative Pre-trained Transformer. Trained on books, it wrote coherent text and generalized across tasks. It handled tasks it wasn't explicitly trained for. Zero-shot learning. In 2019, GPT-2 scaled up dramatically. Same approach, much bigger model, much more data. It wrote articles, poems, even code that felt human. OpenAI paused full release over misuse risks, sparking debate. Even smaller releases showed the world the potential. The trick was no longer a trick. Something big was happening, and it was just the beginning. In 2020, GPT-3 arrived, over 100 times bigger than GPT-2. 175 billion parameters, trained on web and books. It cost millions to train, and the performance jumped. Then came a surprise. In-context learning. Show a few examples in the prompt, and the model learns on the fly. Natural language became a new way to program. It applied brand new concepts correctly without changing weights. People tried everything: code, websites, recipes, poetry. But GPT-3 was raw, an API for builders, not yet a product. The next step, shape power into something safe and helpful. With better alignment, a product was born. GPT-3 had power, but it needed polish. OpenAI used reinforcement learning from human feedback, RLHF. This created InstructGPT, safer, more helpful, better at following instructions. November 2022, ChatGPT launched as a free research preview. The reaction was immediate and overwhelming. It became the fastest-growing consumer app in history. 100 million users in 2 months, faster than TikTok. Students, writers, programmers, everyone tried it. The public release created a massive feedback loop. OpenAI learned fast how to improve the system. AI left the lab and entered daily life through a simple chat box. ChatGPT sent shockwaves through tech, a code red for many. Google accelerated LaMDA and Gemini. Meta and Anthropic showcased their language models. Microsoft, after a $1 billion investment in 2019, deepened its partnership. Another $10 billion expanded compute. And AI infused Bing and Office. Leaders like Sam Altman, Satya Nadella, and Jensen Huang set the pace. Time named AI's architects Person of the Year. NVIDIA chips powered the revolution. New challengers rose too. xAI, Grok, and others. Google doubled down with Gemini's multimodal push. Sam Altman warned, someone will lose a phenomenal amount of money. Nadella asked, is AI lifting real productivity? The true test? In the early days of large language models, users quickly discovered their incredible power, but also their frustrating limitations. For tasks requiring multiple steps of logic, the models would often rush to a conclusion, making simple, unforced errors. They were like brilliant students who refused to show their work, and frequently got the answer wrong as a result. Then, a breakthrough emerged, not from a research lab, but from the community of users themselves. They found a simple, almost magical trick. Just add the phrase, "think step by step," to the prompt. The effect was immediate and profound. This simple instruction unlocked a new capability known as chain of thought reasoning. The model began to externalize its process, writing out each stage of its reasoning before providing the final answer. By articulating its logic, it could self-correct along the way, dramatically reducing mistakes in arithmetic, spatial reasoning, and complex instruction following. It was no longer a black box. It was a collaborator, showing its work and allowing for a more transparent and reliable process. This discovery marked a pivotal shift in how we interact with AI. This new ability to reason paved the way for the next evolution: agents. If a model could create a plan, why couldn't it also execute that plan? The concept of an AI agent emerged, a system that could understand a high-level goal, autonomously break it down into a sequence of executable steps, and then select and use the right tools to get the job done. The LLM was no longer just a conversationalist, it was becoming a conductor, orchestrating a symphony of digital tools to achieve a goal. Suddenly, the model's world expanded beyond its training data. It gained access to a calculator for perfect mathematical precision. It could use a search engine to access up-to-the-minute information, overcoming the knowledge cutoff problem. And most powerfully, it could interact with the digital world through APIs, connecting to real-world services to send emails, manage calendars, or book travel. The model was no longer just reasoning about the world, it was actively participating in it. This expansion wasn't limited to the digital realm. When connected to robotics, these agents gained physical embodiment. They could see through cameras, hear through microphones, and interact with the physical world through robotic arms and grippers. An instruction like, "Find the red ball on the table," was no longer a text-based puzzle. It was a physical task the AI could perceive, plan, and execute. As the agent framework matured, new generations of models like GPT-5 and its successors were architected with these capabilities in mind. They featured vastly improved tool use protocols and the ability to process enormous contexts, allowing them to handle more complex, multi-step tasks without losing track of the original goal. These advanced models also developed a crucial sense of cognitive economy. They learned to differentiate between a simple query that required an instant response and a complex request that demanded a more deliberate, multi-step plan. They learned when to answer fast and when to think longer, invoking tools and chains of reasoning only when necessary. The result was a leap in practical autonomy. Agents could now execute complex, end-to-end tasks with significantly higher reliability, moving from impressive demos to dependable workflows. This wasn't just about answering questions anymore. It was about completing entire projects. Performance on standardized benchmarks soared. In coding, agents could now debug entire repositories. In mathematics, they tackled university-level problems. In fields like healthcare, they assisted in the analysis of complex data, demonstrating a new level of specialized competence. With these capabilities, the large language model transformed into something far more significant. It became the kernel of a new kind of operating system, one where natural language is the command line, and the OS can not only find files, but understand intent and execute complex tasks across any application. This new paradigm unlocked a tireless digital assistant. You could ask it to plan a detailed vacation, and it would book flights, reserve hotels, and add excursions to your calendar. You could give it a raw data set, and it would analyze it, generate insights, and create a presentation. It could write, test, and deploy code, working 24/7. This vision of agentic AI became the central focus of the entire industry. From established tech giants to nimble startups, the entire ecosystem converged on this single powerful idea. The race was on. New initiatives, both publicly announced and secretly rumored, all chase the same ultimate vision. The goal was no longer just to build a better chatbot, but to create a true digital partner. The paradigm was shifting from simply talking about tasks to actually getting them done. The journey of artificial intelligence began with humble aspirations. We started with tiny networks, simple algorithms learning to predict just the next letter in a sequence. It was a foundational step, a digital echo of how a child learns to speak, one sound at a time. These early models were fascinating academic curiosities, demonstrating a spark of potential, but operating on a scale that feels microscopic by today's standards. Now, that spark has ignited a fire. We have systems that can reason through complex problems, plan multi-step actions, and autonomously use digital tools to find information or complete tasks. They can analyze medical scans, write sophisticated code, and even create art. This leap from simple prediction to complex application represents a monumental shift in capability. Yet, the core idea never changed. Prediction teaches understanding. By learning to anticipate what comes next on a massive scale, across text, images, and code, these models build an internal representation of the world's patterns, its logic, and its relationships. It's a form of emergent intelligence, born from a simple, relentless objective. The catalysts for this revolution were twofold: unprecedented scale and a breakthrough architecture. The transformer model allowed us to process data in parallel, capturing long-range context like never before. When combined with vast datasets and immense computational power, scale and transformers unlocked capabilities few thought possible even a decade ago. This rapid progress fuels one of the most profound debates of our time. Is this true understanding, or merely sophisticated pattern matching? Are these models simply reflecting the statistical patterns in their training data, or are they developing genuine reasoning abilities? The line is becoming increasingly blurry. The conversation intensifies as we approach a potential threshold. Some leading researchers and thinkers say artificial general intelligence, AGI, may be here or very close. They warn that our societal and ethical frameworks are lagging dangerously behind our technical achievements, and that we're not ready for the implications of machines that can outthink humans in any domain. This future is undeniably exciting, promising to accelerate scientific discovery, cure diseases, and solve our most intractable problems. But it also carries real risks. The potential for misuse, the disruption of economies, the erosion of privacy, and the challenge of ensuring these systems remain aligned with human values. Navigating this duality requires a global effort. We need robust public conversation that moves beyond hype and fear. We need smart, adaptive regulation that fosters innovation while establishing clear guardrails for safety and accountability. And we need widespread education to build AI literacy across all sectors of society. As AI augments and automates tasks, we must proactively plan for the future of work, skills, and opportunity. This means investing in reskilling programs, redesigning educational curricula, and creating social safety nets to ensure a just and equitable transition for everyone. The goal is not just productivity, but shared prosperity. This isn't just for engineers, policymakers, or CEOs. The choices we make about AI will define the fabric of our daily lives, our economies, and our societies for generations to come. It's a conversation for artists, teachers, parents, and workers. It's for all of us. The history of ChatGPT is more than a story of algorithms and data. It is a tale of human invention, curiosity, and the relentless drive to build tools that extend our own capabilities. It's a mirror reflecting our collective knowledge and, potentially, our collective wisdom. Now, the future of AI is a story we are all writing together. It is an open-ended narrative, not a predetermined script. Our actions, our choices, and our values will serve as the prompt for the next chapter of human history. The power to shape this technology is in our hands. So, what kind of future will we choose to build?